Hello and welcome to GCSE Chemical Changes with Mrs. Castanera. This is Lesson 4, Displacement Reactions. So our keywords today are displace, oxidation, reduction, smelting, or compound and solution. So your first activity is to pause the video whilst you complete the 8 knowledge check questions, please. So let's go through those questions. Question 1. The type of atom formed by a metal atom is a positive ion. Why do metals become ions? Well, because they lose electrons. Name the electrons in the highest energy level. Well, they're called valence electrons. Question 4. Name the two non-metals in the reactivity series. That would be carbon and hydrogen. You need both to get the mark. Question 5. Name the most reactive metal in the reactivity series. That would be potassium. Question 6. State the charge of the nucleus of an atom. That would be positive. Question 7. Name the force of attraction between electrons and the nucleus. Electrostatic attraction. Question 8. Name the least reactive metal in the reactivity series. That would be platinum. So give yourself a mark out of 8 for this, please. We've already done these a few times, so you should be getting a good 7 or 8 out of 8 at this point. So today's overview of the lesson. By the end of the lesson, we should be able to predict the outcome of a displacement reaction, and we should be able to describe the relationship between reactivity and the discovery of metals, which we've talked about briefly before. So displacement reactions. More reactive metals can displace or take the place of less reactive metals when they're in a compound that's usually in a solution. So more reactive metals will displace a less reactive metal from a compound, and that's usually in solution. There are also two non-metals, carbon and hydrogen, that are included in the reactivity series, and we use this list of metals and carbon and hydrogen and their order of reactivity to make predictions about reactions. First of all, we're going to predict whether the reaction is even going to take place. And secondly, if the reaction does take place, we're going to predict the products of that reaction. So this first sentence is the definition of a displacement reaction. So if you're asked a question, say, define a displacement reaction, it is when a more reactive metal takes the place of a less reactive metal in a compound. So moving on to solutions. A metal in solution, which means it's dissolved in a liquid. So this metal in solution, dissolved in liquid, means that the ions from the compound are freely dissolved. So for example, sodium chloride, that's table salt, it's literally the salt you put on your chips. It forms a giant ionic lattice. We're going to look at that in a minute, but only when it's solid. However, in solution, the sodium and chloride ions, they are free to move around. They're still ions, but so they're still ions because they've gained or lost electrons. So they're ions because they're positively or negatively charged because of their losing or gaining of electrons. So they have a charge. So because they're ions, they have a charge because they've lost or gained electrons. So we're going to move on to the notes page here, which for this lesson is page 31. So what we're going to do here, we're going to need a pen, pencil and a ruler and two different colours. They can be highlighters or colouring pencils, however you want to do this. So we take our ruler and we're going to divide just the top section of this page into two, like so. And you'll see that that hasn't gone down very far. I've stopped it just here. So we're then going to turn this into like a table. And on each side, we're going to write in our title. So on the left-hand side, this is a ions in solution. And on the right side, we're doing a giant ionic lattice. So ions in solution, that's a metal compound in a solution or liquid, so it's been dissolved. And this giant ionic lattice is a metal compound, but simply as a solid. Now we're going to draw some diagrams to show this, which you will need to copy out. So here, using a pencil and a ruler, I've drawn a beaker, and inside my beaker I have a solvent. My solvent could be a variety of substances, such as water. Each of these small circles is representing an ion, and there are two types of ion here. We're going to do salt for this example. So salt has sodium ions, which are Na+, and it has chlorine or chloride ions, which are Cl-. And so we're going to label all of our particles, all of our ions in this way, like so. Then, just to make it even clearer, we're going to use a highlighter or a pencil to colour them in or to make them obviously different. So now we can see very clearly that these are two different types of ion, negatively or positively charged, and they are freely and separately floating around inside the solvent. So make sure that you have drawn all of those. I've written that sentence out that I've just explained. So make sure you've got all of the information, all of the diagram, all the labels, and the sentence at the bottom, please. Pause the video if you need to whilst you do this. Then we're going to move on to drawing the giant ionic lattice. So now moving on to our giant ionic lattice, we're going to draw a diagram to show the compound as a solid when it is not dissolved in water or in any solvent. So you can see in this diagram for the metal compound as a solid, we've got a giant ionic lattice, and this shows us the oppositely charged ions alternating, and they're closely bonded together, and that's through ionic bonding, and it has a very giant structure. This is just a tiny section of it. This would continue for millions and millions of ions. And so the positively charged atoms or ions are surrounded by lots of negatively charged ions, and the negatively charged ions are surrounded by lots of positively charged ions. And this is the ionic bonding, where the positive and negative charges, the electrostatic force between them, pulls those opposite charges together, keeps it strong and well bonded together, and that is ionic bonding. So we're going to write a note about this. Okay, so we've written that sentence out, they've just explained. So the oppositely charged ions, that's the positive and negatively charged ions, are closely bonded together via ionic bonds in a giant ionic structure. And here I've put everything we've just done there into one screen, one frame, so you should be able to copy anything you need out in terms of information. So if you need to, again, you can pause the video whilst you get anything you've missed written out. So once you've done that, we're going to go back to the booklet to page 26. So we're back to the booklet on page 26 now. So as you can see, we were here at solutions, and we'd looked and talked about our giant ionic lattice and how the ions look when they're moving around in solution. And so we need to write a little note here to say, see our notes on page 31 or on our notes page. Or if you've just written this on paper, then that's fine. So moving on to reactivity and reactions. A more reactive metal will lose its valence electrons much more easily than a less reactive metal. And we know this, we've talked about this. And remember, valence electron is simply the outer electron in the outer shell, or outer electrons in the outer shell. So, therefore, in a solution that already has metal ions in it, so a solution that has these metal ions in it, it will revert back to atoms if a metal is added that is more reactive. So for example, if we have a solution of copper sulfate, in the solution we have ions of copper and ions of sulfate. Now if we add a more reactive metal such as iron, not ions but iron as in iron, Fe, the Fe, the iron, will lose its electrons more easily, and we convert the copper ions back into copper atoms, leaving us with Fe plus, so positive ions of iron, Fe, and negative charged ions of sulfate. We can draw a diagram to show this. Okay, so I've added a note, so see the diagram on page 31, and then we're going to go back to our student notes page to show this reaction. So we have our student notes page, and we've been working on the lattice and solutions. So we're going to draw a line underneath that with a ruler. draw our new section now about our displacement reaction. So we're going to add a title to this, Displacement Reactions. So please do the same. So I've written a sentence about displacement reactions that I'd like you to write as well. It says that more reactive metals can displace, and I've put in brackets that means kick out or replace, less reactive metals from their compounds. And then we're going to draw an experiment that shows this reaction. If we're in the classroom, I demonstrate that experiment for you, but unfortunately, due to this being distance learning, that's not something I can do. So using a ruler to draw the sides, and then joining up the two lines with a U shape at the bottom and putting the little curves in at the top, we're going to draw our two test tubes. Then we're going to draw a nice arrow between them to indicate that a reaction has occurred. I'm going to label it displacement reaction. And in both the test tubes, we're going to draw a nail, the kind you hammer into wood. So as you can probably see, I did not have a blue colouring pencil or a blue highlighter, which would have been better in this instance. So what I've done here is we've labelled the iron nail here, written a label for that, and I've coloured that in grey. You could have used a pencil, and here I've labelled the blue copper sulfate solution, and that's a blue solution, and it has the copper sulfate dissolved in it, which appears blue. So this contains copper ions and sulfate ions. Then our displacement reaction occurs between the iron metal, so the metal iron here, and the copper sulfate in solution. And what happens is the iron displaces the copper from the sulfate solution. So let's write that down. So the iron displaces copper from the sulfate solution. And now, instead of having an iron nail, we have an interesting different situation. We have copper metal deposited on the iron nail. So it looks very orangey. Okay, I'm going to use a highlighter this time. So it's a very orangey nail now. It's no longer iron. It's very rusty coloured because that's the colour that the copper is deposited on. Okay, so it can be quite shiny, orangey coloured substance on top of that nail that's been deposited. And so the solution of blue copper sulfate becomes iron sulfate solution, and iron sulfate is green solution. So now we have green iron sulfate. So here we have our full reaction. I'm going to zoom in slightly so you can see that better. So we have our blue copper sulfate solution with our iron nail. The iron displaces the copper from the sulfate solution. This is a displacement reaction. And the solution turns green because it is now iron sulfate solution instead of copper sulfate. And the nail becomes copper coloured and shiny. And that's because the copper metal deposits onto the nail. And we're going to label this before and after. So this is before and after the displacement reaction has occurred. So please make sure that you have got all of that information written out and drawn out, and then we can move on back to our booklet. So pause the video if you need to still finish that, and then we can move on to the rest of the work. So we're moving on to page 27, predicting displacement reactions. So your task is to complete the table below by placing a tick or a cross to show whether you think there will or will not be a reaction. And you will need to use your copy of the reactivity series to help you. So we've got some crosses in here already because we know that magnesium is not going to displace magnesium sulfate from its solution because it's the same metal. Same with zinc and zinc sulfate, and iron sulfate, and copper sulfate. So the metal that comes in must be more reactive than the metal in the compound in order for it to displace. And you can find that out from your reactivity series, which we have a copy of at the beginning of our booklet and earlier on in lesson 2. So pause the video whilst you work out whether it will react with a tick or not react with a cross, and then we'll go over this together. Okay, so let's go through that. Now, These are written in order of reactivity. So the most reactive is magnesium and the least reactive is copper. Okay. And again here, the most reactive is magnesium and the least reactive is copper. So that will help you, or will help you to remember this. Okay, so the less reactive metals cannot displace a more reactive metal. So if magnesium is the most reactive, it is going to displace everything that is less reactive than it. Okay, so we're going to tick all three of these. Zinc is not more reactive than magnesium, so it cannot displace magnesium from the compound. But it is more reactive than iron and copper, so it can displace these two. Now, iron is less reactive than magnesium and zinc, so it can't displace those. But it is more reactive than copper, so it can displace copper. Whereas copper is less reactive than all three of the metals, so it cannot displace any of them. So there are 12 marks available here, so give yourself a mark out of 12. Now, normally we would carry on and actually do all these reactions, but of course that's practical activity and we can't do that. So we're going to move on from this activity onto the next page, page 28. So moving on to the checkpoint question on page 28, we want you to compare the displacement reactions of halogens and metals. Okay, so these are the displacement reactions of halogens and metals, and your job is to compare them. So in your answer, you need to include ideas about oxidation and reduction and refer to the two following equations. Okay, that's worth 6 marks. This is a comparison. Okay, so pause the video whilst you have a go at that and do your best attempt at this. Remembering there are marks for all the things we've highlighted. So displacement reactions of halogens and metals, using these two examples as equations and talking about oxidation and reduction and a comparison between them. So pause the video whilst you do that now. This might take you a while. Okay, so there is a lot you can write for this answer, and it's quite tricky to mark, but I've given you some examples of things that would gain you marks. So first of all, you could say that in both reactions, the more reactive element displaces the less reactive element from the compound, and that would get you a mark. In fact, every individual sort of bullet point here would give you a mark. So that's worth a mark to say that the more reactive element displaces the less reactive element from the compound in both cases. Then you could say that that leaves the less reactive element as a product, so the bromine for this one and the copper for this one, and that would be worth a mark too. You could also say that the more reactive element is left inside the compound or as part of the compound, so chlorine becomes part of sodium chloride and magnesium becomes part of magnesium sulfate. So it doesn't matter how you've written it, as long as you've written something that's like this or that says the same thing as this. Then you could talk about that the halogen is reduced, so it's a reduction reaction for the halogen, so that the atoms each gain an electron. Either of those things you could get a mark for. And then for the metal reaction, the reactive metal, or the more reactive metal, is oxidized, or its atoms lose electrons. So you can have a mark for that as well. Okay, so moving on, then we could talk about how the reactivity of halogens is based on its tendency to form negative ions. Okay, whereas conversely, you could say that the reactivity of metals is based on its tendency to form positive ions. So they form opposite ions of opposite charge. Now, for halogens, the closer the outer electron, that's the valence electron, to the nucleus, the more reactive the halogen. So the closer the outer atom is to the nucleus, the more reactive a halogen is. Whereas for metals, the opposite is true. The further away the outer electron from the nucleus, the more reactive the metal. Okay, so there's a lot of points there. There's like 9 different marks you can get there. It's a maximum of 6, okay? So for each of those points that you've written, give yourself a mark up to a total of 6. It would be marked slightly differently in the exam, but it's not really possible to do that at this point. So what I do want you to do is I want you to make sure that you have written out each of these points. Okay, it can be on lined paper or on the notes page or anywhere in the booklet really. because this is a really important long answer question. It's very typical of the ones you get. Now, it was quite tricky, but in some respects you could have earned marks several different ways, and even earning 2 or 3 marks is very helpful, because often there's only maybe 5, 6, 7 marks between grade boundaries. So gaining a few marks here is a whole half grade boundary potentially. I mean, if you get full marks on this, that's a whole grade extra potentially. So it's very easy to earn a few marks on this, even if you are struggling to get a good solid 6-mark answer like this. So do write these out, and hopefully you'll be able to remember them and learn them. And then if you were to be given this question again, which you never know, you might be, but this has happened before in booklets, then you'll be able to give a much better answer next time. So pause the video if you need to write this out. So we're moving on now to the discovery of metals and their reactivity. So the discovery of metals by human beings has developed over time. The least reactive and most stable metals were discovered first, which is not surprising because they were found as single pieces of metal, or which is called native. Let's write that in. So they were found as single pieces of metal. Another way of phrasing this is native or unreactive. And then after that, they were extracted from their ore, which has happened very easily. So only the ones that were easy to extract from their ore were discovered earlier, and those were only the most stable metals. So more recently, we've discovered metals that were harder to extract from their ores. Okay, so these are more recently discovered, because only recently have we had the ability to extract these more difficult ores from these more difficult metals from their ores, and that's because they are more reactive and they require some very complicated techniques for extraction. So we're going to have a look now at this discovery of metals. Okay, I'm going to divide it up into a few sections. So we're going to zoom out for this. So you can see here that on the left here I've labelled earliest. So these were the ones that were discovered earliest and found earliest, all the way through to recent. These are the ones that were most recently discovered. I'm going to write some annotations at the bottom here. So these 3 are found native. So they were simply lumps of metal unreacted in the ground. They would look shiny, maybe the rain would wash away the dirt and expose them. So gold, silver and copper. Then we move on to sort of the Iron Age period. So this here would be the Iron Age, when iron was discovered and used. And that's a very simple form of extraction from the ore, which is reduction by carbon and heat. And we'll talk about that again in a lesson or two's time. So these metals could be extracted from their ores by reduction with carbon and heat. Okay, and so carbon was very easy to come by. They would use charcoal essentially, or even just the charred embers from a fire, and in heat. So they would have carbon and heat, and they would put the two together, and that would produce the metal very easily. And then lastly, from potassium and aluminium onwards, and many other metals, we had to use a very different method using electricity, and this is called electrolysis. And not only did we have to use the electrolysis, sometimes we could use the electrolysis in a solution, and that would be able to remove the ore. And sometimes we had to have not only just the electricity for the electrolysis, but we also had to have the technology to melt that metal, which is very, very high energy, high temperature reaction. So electrolysis of molten compounds. So to have the technology to melt rocks essentially is quite tricky. So you need to melt rocks and then use electricity to remove the metal from that rock, that ore. So that's our timeline, the 3 different types of removal of metals from their ore. So until the 17th century, we only knew of 12 metals, and their discoveries lead to certain eras in history, such as the Bronze Age, which varied in duration depending on where the metal was discovered in each area of the world. So we've talked about the Iron Age, which was around about this time period in the world, so about 1500 years BC. So we're talking about 3,500 years ago. So we're going to move on to page 29 now. So, extracting iron, the Iron Age. So the extraction of iron from its ore by smelting led to the Iron Age, which was approximately 1200 BC to 600 BC. Very much approximate. Okay, so what is smelting? Well, smelting involves heating the ore along with a reducing agent, which typically was carbon, which displaced the metal from the rest of its compound. And there's a video to watch here to help you understand this and learn more about it. So if you've got a digital copy of this booklet, you can just click on this link and it will take you to the page. Or you can go to YouTube and you can type into the YouTube search bar, Fuse School, Extraction Using Heat. Or you can even go to YouTube, find this Fuse School channel and then type in extraction using heat and you will find their video that way. So pause the video whilst you watch that and then come back. Okay, so hopefully you've learned some more about extraction using heat and all about that reaction. So in the example, carbon is more reactive than iron. Okay, that's really important to know that. And so it displaces the iron from its ore because it is more reactive. And the ore is iron oxide. Now, metals below iron in the reactivity series can't do that. So we're going to complete the reaction below for the displacement of iron to form iron oxide by carbon. Okay, so we're going to complete the reaction and we're going to check if it requires balancing. So pause the video, have a go at completing this reaction. We're going to use chemical symbols. Okay, so for carbon, you need to look at the periodic table and see what the symbol is. And for all the other ones, and then you need to check if you've got exactly the same number of elements on the left side of the equation on here as is on the right side of the equation. So pause the video whilst you do that, please. Okay, so let's go through that. So right now we have the unbalanced version of this equation, so step one essentially. So if you have written in FeO for iron oxide, you can have the mark. Capital C for carbon, make sure that for iron oxide your E is lowercase and the F and O are capitalised. Again, Fe for iron, capital F, lowercase e is the only accepted version. And CO2 with a capital C, capital O and a small 2 here. So there are 4 marks available for this part. Now I'm going to go through how we work out whether this is balanced or not. I'm going to use a pencil for this to help us do this. So I'm going to start with iron. We have 1 iron here and 1 iron here. So that's good. It looks balanced to start with. Oxygen, we have 1 oxygen here on the left and on the right we have 2 oxygens. So that's not balanced. Because we have 2 on this side, we need another 1 on this side. So we're going to put a 2 in front of this now. So now we have 2 oxygens and 2 oxygens. That balances. However, we now have 2 ions on this side and only 1 ion on this side. So we're going to put a 2 in front of this ion as well. So we've got the right number of ions, yes. We've got the right number of oxygens, yes. And then carbon, we have 1 of them and we have 1 on this side. So that is now balanced. So you can go ahead now and write in the numbers on top of the pencil. So 2 FeO plus carbon turns into 2 Fe and carbon dioxide. Okay, so you can now have another mark for writing 2 in each of those 2 spaces here. So that is now a mark out of 6. So give yourself a mark out of 6 for that, please. So normally at this point we would do a demonstration showing what happens when you reduce copper using carbon. Unfortunately that's not something we can do. You're very welcome to put a search into YouTube, literally type in reducing copper using carbon and that would show you how to do this, but it's not something I can show you from remote learning. So we're going to move on to the knowledge check. We're on page 29. There are 8 questions and I would like you to pause the video whilst you complete the questions, please. Okay, let's go through those. Question 1. Name the list of metals in order of reactivity. Well, that's the reactivity series. Question 2, describe the metal ions in a solution. Well, we would describe them as freely floating ions or freely moving around, separate, anything like that. Question 3, metals become positive ions. Question 4, explain why some metals have only just been discovered. So, they're more reactive is an acceptable answer, or they require complex extraction techniques is another answer. Okay, so either of those will give you the mark, but you only have one mark. Question 5, complete. More reactive metals, well, they displace less reactive metals. Question 6, name the earliest discovered metal, that would be gold. Question 7, name the process used to extract iron from its ore, smelting. Question 8, name the element used to remove iron from its ore, carbon. So give yourself a mark out of 8, please. Okay, so moving on to the application of knowledge questions on page 30. Suggest a suitable element to remove aluminium from its ore, aluminium oxide. Well, remembering you need a more reactive element to remove a less reactive element from its ore. In reality, the element you suggested in question 1 is rarely used considering where it lies in the reactivity series. Therefore, alternative methods of extraction are used, which we'll be covering in a later topic. Suggest why the element used is not used to extract aluminium from aluminium oxide. So pause the video whilst you have a go at these questions. Okay, so let's go through those. So for question 1, a suitable element to remove aluminium from its ore would be anything higher than it in the reactivity series. So that's magnesium, calcium, sodium, and potassium. So any one of those you can have a mark for. Question 2. So in reality, the elements we listed above are rarely used because they're more reactive in the reactivity series than aluminium itself. And there are all alternative methods of extractions that we use, which we've already discussed. This is electrolysis. So suggest why the element you used, or you suggested, is not used in the extraction of aluminium from aluminium oxide. There's a few options here for your answer. You could say that all of these metals, or the metal that you stated, requires electrolysis to be extracted from its ore. Okay, so that's an acceptable answer. So you can have a mark if you said something along the lines of the metal that I've suggested needs electrolysis or to be extracted from its ore. So you can also say that your element, your metal, is more reactive than carbon and difficult to extract from its ore, so it doesn't make much sense to use it then to extract a less reactive element. Or you could say that it takes more energy to extract a more reactive metal, such as magnesium, calcium, sodium, potassium. So you could just use less energy to extract aluminium itself first instead, rather than spending the energy extracting the higher reactivity element to then extract this less reactive element. So anything along these lines is a perfectly acceptable answer to this question. So we also have this lesson, some keywords, smelting or compounded solution. You need to learn the definitions for those, please. That is the end of our lesson. Thank you very much. If you have any questions, feel free to email your teacher or myself. We'll be very happy to help you.